So let's consider a linear map that's not necessarily an isomorphism. So it might not be one-to-one, it might not be onto. So let's draw a picture of what's going on. Here's B, here's W. So any vector V here is mapped to some vector W here. In other words, if there's one arrow coming from V going over here, there might be more. There might be like another vector here going to this one. One thing is I do know is that the zero vector in V goes to the zero vector over here, okay? Well, I can collect together over here all of the vectors that are images, and I can call that the range space. Is the set of all images of vectors in V. Now that could be, the range space could be large or small. For example, I could have the map H that maps every vector to the zero vector. So then the range space would equal just the zero vector. So it'd be very small, which would, and so on the other hand, it could be that the map is onto and so the range space could be, it could for a different map be the entire space W. So range space could equal the zero space in W, or all of W, or something in between. Okay. So it's going to turn out that it's called a range space because it's called a space because the range space is not only a subset of the codomain, it is also always a vector space. Okay, so why is that? Well, the point, if it's a subset of the codomain, how do we know it's a vector space? Well, it's a subset of the codomain. We can let's choose an arbitrary vector W that's in the range space. And ask, well, if it's in the range space, there's got to be, if it's in the range space, that means that there's a V such that f of V equals W. Okay, well, the question is, well, actually, we want to be a little bit, we say, okay, we know it's a subset of the codomain, but it's a vector space. How do we know? It's true that if I choose an arbitrary vector in the range space, I know that there's a V such that f of V equals W, but that's not quite the first point to make. The first point to make is we'd like to know is, we know that W is an arbitrary vector in the range space, but is it is it true that if I take two of these arbitrary vectors, W1 and W2, that are in the range space, is there linear combination in the range space? That's the range space test. So I take R, W1, S, W2, an arbitrary linear combination, and ask, is this in the range space just because W1 and W2 are? Well, let's see. That means that this has to be the image of some vector in the domain. Well, since W1 equals f of V1, and because W2 equals f of 2, because there have to be vectors V1, V1, and V2. This happens because W1 and W2 are in the range space. We want to show that this is in the range space. Well, this vector equals, for arbitrary R, S, and W1 and W2, f of V1 plus S, f of V2. But f is linear, so that's equal to f of R V1 plus S V2, and there it is. There's a vector in the domain that maps to this one. So that means that the range space is a vector space. Because the range space is a vector space, it has a dimension. We can find a basis. So the dimension, the number of vectors in a basis of range space, is the rank. Is said to be, is called, let me see, is called the rank of the map. Now, it's going to turn out that this rank of the map is going to be related. We've seen the word rank before in terms of matrices. For a matrix, the rank of a matrix was the number of linearly independent rows. It's going to turn out that the matrix that represents a map with a given rank will have the same rank. So it's going to be a connection between the rank of a map and the rank of a matrix. Okay, well, how do I find? Let's say that I'm given a map like, well, let's say we're given a simple map. Let's say I'm given the map M from, say, X, Y, Z, that goes to X plus Z, Y plus Z. How do I find the range space? Well, the range space is all of these. So you take all the images, you say the range space R is equal to all the X plus Z, Y plus Z, such that X, Y, and Z are any real numbers. That's what you mean by the range space. It's just all of these for arbitrary X, Y, and Z. Okay, so this is one of the first, this is now, but to find the range space, what we mean is to write, this is sort of the definition, but to write this as the span of a vector, span of a set of vectors. Because we'd like, if we want to find the rank of this map, we need to find a basis for the range space. We have to write this as a span of vectors, then see that those vectors are linearly independent. So I can write this as X times 1, 0 plus Y times 0, 1 plus wait. I miss, this is X plus Z, Y plus Z. So I have X, Y, and Z times 1, 1, such that X, Y, and Z are members of R. Okay, so I can see that I've written R as a span. So I know these three vectors span the range space. but do they form a basis? Well, you can see that this third one is a sum of this first and second one, because 1, 0 plus 0, 1 equals 1, 1. That means this is linearly dependent on the other two. Now, I know that I can remove a linearly dependent vector from a set and span the same space. So we can say this is the same as x times 1, 0 plus y times 0, 1, such that x and y are any real numbers. And that forms a basis. So that so this is a basis for range space. Therefore, the rank of the map M equals 2, because there's 2 vectors in the basis. It has nothing to do with the components, it's the number of vectors here. And you can see that that is the first bit. What is the range space? What we mean by the range space is exhibiting it as a span of a basis vectors. What is the rank? Well, the rank is 2. So what you'll do on this assignment is, like for this first one here, you'll take the set of all of these and write them as a span, and then decide whether linear independent, get a basis, and you'll find the rank. And the same thing, you do that here, and you do that here, and with this map, and then you can, this is something else. But along the, so these are something else when you get to 6 and 7. So that's a big part of the next assignment, is to find the range space and the rank. And we can practice that a little bit today. And there's one other bit of the story. Let me